We've done some with springs now, and we've done properties of waves, so now we're going to start putting these together. This is going to be a video about simple harmonic motion. Simple harmonic motion is what happens when we have periodic motion that perfectly repeats, where we have something that obeys Hooke's law, and where we don't have anything that dies down over time, so we don't have friction or anything like that. So if we've got something like that, one big example of this that we see is a mess on a spring. And when we do this, we like to have a floor here that has no friction. This has a spring constant and maybe an equilibrium length here. I'm going to mark it at the right side of this box because it's a little bit easier to mark differences from an edge than it is from the middle. So I've got this, and now I'm going to take this thing and I'm going to stretch it out to here instead. When I do that, I have moved my system to the right. If I take it to that position and then I release it from rest, then that means it's not going to get past here. Right now, when I stretch this out and it's not moving, when I stretch this out, I'm giving this some amount of potential energy. If I give it no kinetic energy, then that means all of the energy it has is potential. As soon as I let go, it's going to start moving back to the left. And if it moves back to the left, that means it's going to be losing potential energy, gaining kinetic energy. That's now going to get to the equilibrium position. When I get to the equilibrium position, I have a displacement of 0. So I have no potential energy left. All of my energy is kinetic. And then I'm going to compress because I'm moving now. I don't just come to an abrupt stop, right? Then my kinetic energy would be 0 also, and all my energy is gone. That doesn't make sense. It has to go somewhere. So this thing starts out here at this distance from rest, and then it starts speeding up. It keeps speeding up until I hit the equilibrium position. I fly right through the equilibrium position, and once I'm out the other side, now I'm past equilibrium, and I start to slow down. I will keep moving and moving, slowing down farther and further, until I reach the same compression distance as my original stretch. At that point, all my energy will be potential again, and I will have come to a stop. And I'll just bounce back and forth between those. Because that's the outer limit of where I'm going, that means this initial stretch must be my amplitude. So I want to look at a couple of things. First, my total energy. My initial potential energy is half k times my initial position, which is the amplitude we just said, squared. In the beginning, at that location, all of my energy is potential. If I were to graph this thing, I would say out here, if I were to graph this, and I said right here, let's call this my x equals 0, then this oscillator is going to go back and forth between x equals a and x equals minus a. This is my x-axis then. If I am plotting energy, then I'm going to have potential energy that over here, this is a half kx squared, that's a parabola. So over here, I'll have something like this, and that's going to be symmetric across the x-axis. This is my potential energy. Now my total energy has to be constant. So over here, I will have no kinetic energy. In the middle, I will have all kinetic energy. I'm going to have to move my axis, label anyway. But what I get is something that looks like that. If I take my total potential energy and my total kinetic energy and add them up, I get one set energy value the whole way across. So my total energy, this is total energy, and red was my kinetic energy. My total energy, which is potential plus kinetic, stays constant. My initial potential energy is my total energy. This is my energy budget. At equilibrium, so this is out at x equals amplitude. If I want to look at equilibrium, then my potential energy is 0. And my total energy is, the sum of potential plus kinetic, but potential is 0. So my total energy will be kinetic. If all of my energy is going into kinetic energy, I will be moving at the maximum speed that I can. So at x equals 0, I'm going to get all speed. These are both equal to my total energy, so they must be equal to each other. So I'm going to have a half k a squared equals a half m Vmax squared. I'm writing Vmax in red because that's the quantity that I'm solving for. K is a spring constant. That's something that I can measure. Mass I can measure. Amplitude, that's easy to measure. I can take a picture and measure that one. But measuring a speed, that's a little bit tougher. So let me solve for Vmax. My halves go away, and I get that my Vmax is equal to K over M under square root times the amplitude. Well, that's helpful. Maybe I can get some more values like this. What else can I get? My maximum position, well, that is just the amplitude, so that's convenient. And let's look at my force. My force I know is mass times acceleration. So my maximum force is mass times maximum acceleration. And my maximum force happens at the amplitude. If I solve this for my maximum acceleration, I get k over m times a. So I have something interesting here. I've got this equation for my maximum position, this one for my maximum speed, this one for my maximum acceleration. So it would be really great if that k over m were a quantity that I could work with, and it is. K over m happens to be equal to the square of the natural frequency, which means I can write this set of equations really cleanly. I can say my natural frequency is square root of k over m. My x max is a. My v max is omega a. And my a max is omega squared a. It's an easy set of equations to work with. I can do just a little bit more because sometimes I don't know the spring constant and the mass. But maybe I'm told that I have a mass on a spring and that my mass if I'm starting this from rest, I'm starting out here. Maybe I'm told that my mass behaves like this. And I'm told that, so this is y, or I guess x if it's horizontal, versus t. And maybe I know that my system is released from rest at x equals 10 centimeters. And it first passes through equilibrium after, maybe a half a second. what can I do with that? I have here part of a wave. It's going just from the top back down to 0. If I take this part of my wave and cut it in half, well, this is exactly the same as this, which means this one happens at 1.0 seconds. Over here, I get this again, so this must be 1.5 seconds. And over here, a half wave gets me, or a half second gets me back up to the amplitude. This is just utilizing the symmetry of waves. So this is a half of a bump. Here's a half a bump, a half a bump, a half a bump. So that's 4 total bumps. This isn't a half a second. This is a half a second farther than where I was, so that's 2 seconds. Well, I now have the amount of time that it takes to go from the top to the top again, and that is my wave period. If that's my wave period, I can get the frequency. And if that's my frequency, I can get my natural frequency. It might throw you off to have pi in there. We can think of pi when you see pi in here. Just think to yourself, oh, that's about 3. Because sometimes seeing that as a number helps out a lot. So now if I want to find my maximum position, well, my maximum position, that's just the amplitude, that's going to be 10 centimeters. My maximum speed, pi, radians per second, times 10 centimeters. So pi is really like 3.14 radians per second. But it keeps going anyway. If I'm going to say that pi is 3, bear with me on that, 3 times 10 centimeters is going to be 30 centimeters per second. Or if you like 0.3 meters per second. Omega squared, well, if omega is 3, 3 squared is 9, times 10 centimeters, this is going to be 90 centimeters per second squared. Or, you know, we can write these a little bit differently. We can say this is 0.3 meters per second, and this is 0.9 meters per second squared. What I want you to see, I was given this much of a graph. And I wasn't given information about the spring constant or the mass. But with that much of a graph, I was able to get my maximum speed, my maximum acceleration. I can do all of those pieces. So I can use the same couple of equations and this definition of omega along with my wave properties to be able to figure out a whole lot of things without too much trouble.